Hello, everyone. I would like to tell you about our work, which is titled Single Trusted Qubit is Necessary and Sufficient for Quantum Realization of Extremal No Signaling Statistics. My name is Ravi. I work at the University of Hong Kong, and this work was done in collaboration with Michal Banatsky, Ricardo Rodriguez, and Pavel Horodetsky from the International Center for Quantum Technologies at the University of Gdansk. It's posted at this location, so I encourage you to read this paper after listening to this talk. So a brief motivation for the work. Well, you know that the violation of Bell inequalities or steering inequalities essentially shows that quantum theory differs fundamentally from all classical theories. In particular, we also know that quantum correlations allow to perform tasks that are impossible in classical theory, such as the generation of cryptographic key secure against general eavesdroppers, the generation of certified randomness, reduction of communication complexity, and so on. Now, a useful property in many of these tasks, especially in device-independent cryptography, is called extremality of quantum non-local correlations, meaning that the observation of extremal behavior by honest parties within the set of all measurement behaviors in the experiment guarantees some form of security. In particular, this extremal behavior guarantees that the honest party's system is completely decoupled from that of any adversary. Now, this complete decoupling means that we can then build proofs of security in a much more streamlined and efficient fashion. So in many problems, it's very useful, maybe not completely necessary, but it's definitely very useful to have extremal quantum non-local correlations. Now, in the study of quantum non-locality and DI cryptography, device-independent cryptography, it's also customary to consider general no-signaling systems. The quintessential example being Popescu-Roerlich boxes, but there are many other systems known. So in these areas, one can also consider what's called a no-signaling adversary who is only constrained by the no-signaling principle of relativity. So in the quantum non-local correlation study, we have classical correlations, which are described by the local hidden variable models. Then there are the no signaling correlations, which are the most general correlations that are only constrained by the set of, by the principle of no signaling. And there is the quantum set of correlations, which lies in between these two sets. So this is from a paper by Daniel Cavalcanti, where he shows a very nice illustration of what happens in the case of the CHSH scenario, where you have two players, each performing two binary measurements. In that case, we have the local set, which is depicted here as the square. Then there is the no signaling set, which is depicted as another square. And the quantum set is depicted as a circle here. So of course, the actual sets live in dimension 8 and not in 2 dimensions. But this is a useful illustration to understand what we're talking about. In particular, these Popescu-Roerlich boxes are the extremal points, the vertices of the no signaling polytope, and up to local relabelings in terms of the number of parties or the number of, or the inputs or the outputs. These are the only extremal points in this particular scenario. In more general scenarios, when you have more number of inputs or more number of outputs for each party, we have much more general polytopes and much more general quantum convex sets. And there is a lot of interest in characterizing these sets. And our main interest in this work is to look at whether we can realize these extremal points. So the central question that we are interested in is that can quantum correlations reach extremal points of the set of no signaling correlations? And as I stated, this question is of both fundamental and practical relevance, because the realization of extremal correlations means that we are guaranteed that the system is in a product state with any adversarial system, which means that we can build in a simplified and a streamlined way proofs for many DI and SDI protocols. Now, In a paper from 2016 with Jan Tuziemski, Michal Horodecki, and Pavel Horodecki in PRL in 2016, we showed that if you consider any of the usual Bell scenarios where you have n players, m inputs, and k outputs per player, the quantum correlations do not really reach extremal and non-local no signaling boxes, meaning that if you consider these really non-local boxes, there's no signaling non-local boxes, and if you are interested in extremal points of the set of no signaling boxes, then quantum correlations do not help you to realize any of them. Irrespective of the number of inputs or number of outputs or the number of players in the game, such a point is never realized in quantum theory. So an interesting question was whether such a realization is possible when we consider more general scenarios, such as the scenario of sequential Bell non-locality or that of quantum steering. So the idea is to go beyond the usual Bell studies to consider things like sequential Bell non-locality, where we have correlations between measurement runs that are performed in sequence, or to the study of quantum steering, where one of the systems held by one of the players is trusted, so it's characterized as a particular quantum system. So whether in either of these cases one can really realize extremal correlations of the no signaling set, which in turn will allow us to formulate nice proofs for let's say, whatever DI cryptographic task we are interested in, or SDI cryptographic task. So the first result we show in this paper is that if we look at the general scenario of two-party sequential Bell non-locality, where each party performs an arbitrary number of measurements per run and an arbitrary number of outcomes for each of these measurements, then quantum correlations, irrespective of what dimension or what state or what measurements we get them from, cannot reach the extremal points of the corresponding no signaling polytope, which in this case is called the time-ordered no signaling polytope. Okay, so the precise statement of the theorem is that for any number of inputs for Alice, for any number of outputs, and for any number of inputs and outputs for Bob, that if we have an extremal point of the time-ordered no signaling polytope, which is not also an extremal point of the classical polytope, which would be a trivial realization. So as long as this is an extremal point that is outside the set of classical points, then quantum theory does not help you to realize that, meaning that such boxes cannot be realized in quantum theory, irrespective of what measurements or what state you perform these on. So the next question is whether we can in fact obtain such a realization if we go beyond the setting of non-locality, maybe to consider the setting of quantum steering. So what we do is to consider the scenario of quantum steering in which two distant subsystems share a quantum state, rho AB. So here we have system A, which is uncharacterized, so it's a black box, pretty much like what happens in non-locality. While on the other hand, system B is fully characterized. We know the dimensionality of the hidden space, and Bob can even perform tomography on his system. Now, a measurement is performed on system A, and system B is then described by some set of subnormalized states, sigma AXB, which essentially says that the state sigma is some subnormalized state that depends upon the input X of Alice and the output A of Alice. So depending upon the input that Alice chooses and the output that she obtains, Bob will get some subnormalized state on his system, and this is given by this expression. Now the collection of such subnormalized states, which we denote by sigma B, is traditional to denote by sigma B, is called as a quantum assemblage. Okay, so in the setting of steering, we are not interested in just the probability distributions, but in the set of subnormalized states to which Alice steers Bob's system by performing some measurements on her system. Now, again, in steering, you can consider the set of quantum assemblages, or you can even consider more general no signaling assemblages. Now, no signaling assemblages are essentially similar to quantum assemblages, except that the joint state is no longer described by quantum theory, but by some general no signaling theory. So to be precise, the assemblage in the no signaling sense is simply some set of positive or non-negative operators, sigma AX, on Bob's side, which obey a constraint of no signaling, meaning that for different choice of inputs on Alice's side, if we sum over the outcomes on Alice, then we get the same sigma B, which is some normalized state. Now, the interesting point is that in the bipartite case, if we have just two parties, the set of quantum assemblages and the set of no signaling assemblages are in fact known to be identical. And this comes from a very famous result called the Houston-George-Wouters result from '93. In other words, there is no post-quantum steering in this setting, meaning in this setting, the set of all quantum assemblages and the set of all no signaling assemblages are the same. There is no signaling assemblage that goes beyond the quantum assemblages. So if we really want to realize extremal points of a no signaling assemblage, the interesting question in the steering setting is to consider 3 or more parties. So in this 3 or more parties scenario, it's known that there are no signaling assemblages that go beyond the set of quantum assemblages, and this was shown in this paper by Sainz et al. From PRL 2015. So the question is, can quantum correlations realize extremal no signaling assemblages in the tripartite scenario, steering scenario? And surprisingly enough, in contrast to non-locality, it turns out that in fact we can realize extremal no signaling assemblages by means of quantum assemblages. In other words, there are 3-party entangled states in which you can perform a measurement on Charlie's system, which gives you some assemblage on Alice and Bob's system. And this is a kind of an inflexible and an extremal assemblage. In other words, this is extremal in the set of all no signaling assemblages. And you can show that it's extremal within the set of all no signaling assemblages. And you can even derive a steering inequality and show that it's maximally violated within the set of all no signaling assemblages by this point. And furthermore, it's even uniquely violated in all no signaling assemblages by this point. So our results show that relaxing the setting of DI cryptography to allow for one party to have access to a fully trusted qubit system allows us to obtain quantum assemblages which are extremal within the set of all no signaling assemblages. In other words, this result opens the path towards semi-device independent cryptography against general no signaling adversaries. So because we can realize extremal no signaling assemblages within quantum theory, this essentially allows us to realize points that are decoupled from any no signaling adversary, which means if we go to this setting of a trusted qubit, then we are allowed to, we are able to obtain correlations that are extremal even within the set of general no signaling behaviors. And so we can formulate proofs against no signaling adversaries quite easily in the steering scenario. So this opens up this research area in this direction. So there are several questions also opened up, in particular regarding self-testing extremal assemblages in the set of all no signaling assemblages, extensions to many party and high dimensional scenarios, as well as the characterization of extremal assemblages that admit quantum realization. So we know that there are some extremal assemblages that do not admit quantum realization. So the idea is to characterize those no signaling assemblages extremal that are in fact realizable by quantum correlations. So with that, I point you towards this paper and I thank you for your attention.